Hello and welcome to our first video for acids and bases. This will cover the beginnings of acids and bases and equilibrium regarding acidic and basic systems. And this is a picture I like to show of three organic acids and one not acid. So maybe come back to this in class and see what you guys think when we get a little further in. There's a title page. We're going to cover most of chapter 14 and a lot of chapter 15 in the Zumdahl text, so just stick with me when I roll through this. This is kind of a little bit of review, a little bit of new global picture of acids. So first, I like to just remind you that these are common substances that are present in your everyday life. You taste acids all the time. You taste bases sometimes. Um, and their properties are many, but taste is a good one to go to. And I thought I found pretty good pictures of a kid making a sour face and a kid making a bitter face. So there you go. Three big acid theories sort of govern all of chemistry. The first was the Arrhenius theory, and it was the most narrow of the three. Basically, Svante Arrhenius came to the conclusion that Arrhenius acids produce hydronium ions or hydrogen ions in water, and bases produce hydroxide in water. And though it applied to most substances, there are substances that act as acids outside of aqueous solutions, and so the Bronsted-Lowry system broadens the scope a little bit to where it focuses on simply donating or accepting a proton. And even more broad and actually more appropriate for organic chemistry is the Lewis acid Lewis base definition, which is not part of AP Chem, but I think it's relevant to start to think about it. The Lewis acids accept electron pair to form a new bond, and Lewis bases donate electron pair to form a new bond. So um, you can start to sort of think about these things as we go through looking at acidic and basic systems. We do need to define the hydronium ion. We often think of acids as hydrogen ion systems, but reality is hydrogen ions don't sit free in a solution. It's more appropriate to have them attached to water, and so we do. And water molecules that bind those hydronium become a different structure. Bronsted-Lowry theory again. We look at an acid-base system with a conjugate acid and a conjugate base. Forgive the formatting there. Conjugate bases are whatever remains of an acid molecule after it's lost a proton, after the acid's lost the proton, and a conjugate acid is the base after it's added the proton. So make sense of those definitions. At this point, let's try to identify some conjugate bases. And remember, an acid loses a proton, it keeps that electron. You can look at it from the Bronsted-Lowry or the Lewis point of view there. Keeping that electron effectively, it's now got a new electron pair that wasn't shared in a bond. So hydrochloric acids got the acid definition. This conjugate base would be minus the proton. And so all five of these strip off the proton, leave behind an extra electron for a negative charge, and then it gets pretty intuitive after you've done it once or twice. Notice that conjugate or acids form conjugate base anions, except for a situation like methylamine or ethylamine formation from an ion system, which is rather complicated, but not rather complicated. It looks complicated, but it's rather simple. And we will see a lot of organic bases on free response questions and uh, um, molecule identification to look for things that appear to be basic when we get a little further in. What about conjugate acids though? Conjugate acid is a base after it's gained a hydrogen ion, so fluoride plus a hydrogen or plus a proton will give you hydrofluoric acid. Ammonia plus a proton gives you ammonium, and water plus a proton gives you hydronium. So those should be rather familiar to you. Um, let's define strong acids. Strong acids dissociate completely in water, in theory. The equilibrium of these systems lies very far to the right. Most importantly, you'll see this questioned a lot. A strong acid will yield a weak conjugate base. What does that mean? The conjugate base is weak. Okay, so we'll come back to that. And strong acid dissociation, you should note that we have a single-headed arrow. That's because it doesn't form an equilibrium system. You're considered to have all products and no reactants, so there's no equilibrium, no reversibility component. Weak acids are mostly undissociated. Equilibrium lies far to the left, which means that the concentration of products and reactants at equilibrium is left favored. Has a very strong conjugate base, much stronger than water, but not a strong base. So a weak acid makes a strong conjugate base. And there's a great comparison chart there on the slide that highlights this here, the relative strength of each and the conjugate strength. And it's obviously an inverse relationship. So weak acid dissociation, we should note it's the same reaction, but we see a double-headed arrow, which implies we're going to have an equilibrium system. And that's where a lot of the rest of this unit comes from. We term the weak acid dissociation constant Ka, and for bases it would be Kb, and you'll, just like we have handled that in the past, we'll continue to handle it as acids go, bases go. We have to learn the systems. So once again, hydronium, hydrogen ion, interchangeable. Why isn't water included in that expression? Water's a liquid. Liquids don't get included in equilibrium systems because their concentrations can't change. Weak acid dissociation constant, this is how we describe the strength of an acid. It tells us where equilibrium lies in the system and therefore implies the strength of the acid. Smaller the Ka, the weaker the acid. We won't often discuss Ka values for strong acids because their concentration of intact acid is really small, and the measurements on it are going to be fuzzy. They do have Ka values, even accepted Ka values in the chemistry world, but we won't use them in this course. We'll consider them to be not relevant. You may see them discussed in an anecdote question, but it's not going to be something you're looking for trendworthiness. The tipping point for things that tend to be considered a strong acid are things that have a Ka greater than 1, or any acid system where there's more hydrogen or hydronium ions than intact acid. So sketch what 5 molecules of hydrogen fluoride or hydrofluoric acid, weak acid, and 5 molecules of hydrochloric acid, a strong acid, would look like. So pause, and then, I'm going to give you an example of what I mean by an intact molecule of hydrogen fluoride would look something like this. Here is the anion, and here's your proton. That's an intact. Whereas hydrochloric, it would be not intact. You have a proton and you have an anion. So pause and draw. Okay, welcome back. This is what we came up with, which is kind of cute. It gives a relative size. The protons are all the same size. Fluoride's smaller than chloride. But what you should notice is that in the hydrofluoric acid solution, we see mostly intact acid, and in the hydrochloric acid solution, we see everything dissociated. Conjugate base strength. Okay, so we have Ka values for acetic acid, for hydrocyanic acid, and for nitrous acid. This question is, given the Ka values for the acids above, rank these conjugate bases from weakest to strongest. So what we talked about earlier was when strong acids dissociate, they have a weak conjugate base, and therefore weak acids would have relatively strong conjugate bases. The weaker the acid, the stronger the conjugate base. And so we have here 3 weak acids that we need the Kas for. We also have the conjugate base for hydrochloric acid here, and we have water. Okay, keep in mind the Ka and Kb for water is 1 times 10 to the negative 7th, so relatively important. So let's see which of the conjugate bases is weakest to strongest. So weakest conjugate base, chloride. Oh, I'd hope to give that to you sequentially, but that's okay. Chloride is the weakest conjugate base because it comes from a strong acid. Then we have water, and then we have nitrite, which comes from the nitrous acid, and we have acetic or acetate that comes from acetic acid, and the cyanide ion from hydrocyanic acid. So the weaker the base, the stronger the conjugate. The weaker the acid, the stronger the conjugate base. And so our big winner was this guy. It's an extremely weak acid, so it has quite a strong conjugate base. Now, I think we should define that. That strong conjugate base, what does that mean? That means that in this system, double-headed arrow, proton, cyanide ion, that the system is going to be overwhelmingly hydrocyanic acid intact. What that means is this conjugate base is most apt to snatch up hydrogen ions and form the intact acid. Okay? Or, look at it this way, put it in a system with water, what's it going to do? It's going to grab hydrogen ions and leave hydroxide behind. Okay? So your products in this would be intact HCN and hydroxide. This is called hydrolysis. Weak acids, conjugate bases, are excellent at turning water into hydroxide, and therefore strong conjugate bases. They're not as strong as a strong base, so don't get that idea. But they do have quite an impact on the system to make it basic. So some common strong acids. These are all aqueous solutions, large Ks or negative pKa's if you were to measure pKa. You have sulfuric, hydrochloric, nitric, perchloric, hydroiodic, and hydrobromic. Chloric acid we're used to from prior learning is kind of on the bubble. For this course, it's not a strong acid. We will discuss its Ka from time to time. So now let's talk about sulfuric acid. Sulfuric acid is kind of an oddball. It's diprotic, which means it's got two acidic protons, hydrogen ions that can be lost to form an acidic solution. The first proton, when H2SO4 dissociates, is a strong acid. The second proton coming off when hydrogen sulfate dissociates is weak. And it's, for our purposes, the only acid that's going to do that. Oxoacids are basically acids in which the acidic protons attach to oxygen. Most acids are oxoacids. You're going to see this a lot, especially in organic chemistry. But here's some examples, strong and weak, where we have the acidic proton attached to oxygen. Acid strength trends are very, very important. Within a series of oxoacids, acid strength increases with increasing number of oxygen atoms on the central atom due to the inductive effect. And there you have the perchlorate down to hypochlorite acids, and then sulfuric, and then sulfurous acids, both of which exhibit this increasing acidity with more oxygens on that central chloride or sulfide. So, or chlorine or sulfur, pardon me. And then you see the inductive effect defined for you. Ultimately, what you need to see there is that as you add those electronegative oxygens onto that atom, you further polarize the OH bond and lower the energy required to attract that hydrogen ion away from the acid molecule. Acid strengths also increase with increasing electronegativity of the oxyacid anion. For example, chloride produces a stronger oxoacid than a methyl group would. Organic acids are mostly topical for us. We'll see them in images. We may have to define them based on an image, and so we need to be comfortable with what it constitutes. Most of what we'll see will be carboxylic acids, which are the circled acids here and here. And what you see among them is this: the group attached to the carboxyl group can be any structure that could bond to it. And there are dozens and dozens in organic chemistry, but what holds them similar is this structure here that called the carboxylic acid group. These are all going to be weak acids, obviously, because they're not part of our strong system, and they are too numerous to show. And on the next slide, I'm going to show you a bunch of common carboxylic acids you may have not even known you knew about. There's also another group that's fun to talk about called sulfonic acids, which are even stronger than carboxylic acids in some cases. Mostly because of this fun fact. This one right here is called taurine. Taurine is an amino acid that's present in human and really any mammal's bile. And what's funny is they discovered it in ox bile, and it's one of the substances they put into Red Bull, the energy drink. It gives you wings, evidently. These are the carbon chain lengths for a number of carboxylic acids, and their interesting name But starts off with a 1 carbon, which would be formic acid, a 2 carbon acetic acid, 3 carbon propionic acid, and that's lard you see there because it's in lard, and butyric acid's in butter. It's also or butanoic acid. It's a little bit in butter when butter rancifies, or it's also known as the smell for vomit. Valeric acid present in valerian root, caproic and caprylic, which are in goat's milk, and it goes on and on. It's a really fun list, but I urge you to take a peek. What's important to note when we get into bonding, the longer these carboxylic acid chains get, the more intermolecular force between the molecules, and the more they form solids and things like wax and peanut oil and lard and all sorts of cool stuff. Hobby wax, when you get up to 35 carbons long, beeswax, and many, many more. Hydrohalic acids. This is, to me, is just giving a name to something that doesn't need a name, but if it pops up, I don't want you to be confused. Any binary acid with hydrogen bound to a halogen is a hydrohalic. Hydrohalic that's weak is hydrofluoric. And the definition, or the explanation for why hydrofluoric weak is on this slide. This is important. Why is it weak? Although hydrofluoric acid is a very polar bond, which would lend us to believe that it was polar enough for the hydrogen to depart, it only weakly dissociates because water cannot provide enough energy to break that very short hydrogen fluoride bond in significant concentrations in normal conditions. So that's that. Amphoteric and amphiprotic substance will be our last slide. This is a combo definition, but we're going to stick with amphoteric for our course. And the reason is that when you get into amphiprotic, you're really narrowing your scope. And so amphoteric will take you all the way through organic. But anyway, substances that can act as an acid or a base are considered amphoteric. Okay, that covers everything. This suits even the Lewis definitions, because the Lewis definition doesn't focus on protons. The definition we're going to sort of acquaint ourselves with, but sort of leave there, is amphiprotic. Amphiprotic means that a substance can either donate or accept a proton, which is sort of limited in Bronsted-Lowry theory. So we'll stick with amphoteric to describe acids that can both act as an acid or a base, or accept a proton and lose a proton. And that concludes the video number 1 for acids. We'll see you on the next video.